This lesson deals with a 3-terminal adjustable regulator. You can find these notes in the ECE402 ebook in Chapter 8, starting on page 1. The name of the course is Applications of Analog Integrated Circuits, and we've looked at a couple ICs. Started out with an op-amp, then we took a look at a comparator, and then we looked at a 555 timer. Literally every month there are new integrated circuits, analog and digital, and how do you deal with using them or figuring out how they work? Well, the best place to start is with a data sheet. We're going to take a look at what's called an LM117HV, and was a new IC many years ago. And a good place to start is with the specification to see what it does. But usually when you get a new integrated circuit, the manufacturer is trying to get you to use it, so they put out what's called an application note. And in these application notes, there's usually a lot more detail as to how the IC works. The picture I have here is a functional block diagram for the LM117HV that was in a National Semiconductor application note, number 181. And National Semiconductor was eventually bought by Texas Instruments. So here's a reference voltage, basically like having a zener. Here's a current source to keeping that zener turned on. And then here's an op-amp with a set of power transistors on it, pretty much like we've done in our course, and then putting feedback around it to essentially make this look like an op-amp with a current booster. So the voltage here is roughly going to be the same as the voltage across here. So it's going to force whatever we have out here, a fixed voltage across it, but the current's going to be supplied by another part of the circuit. Let's take a look at the data sheet and the application note. The file that I sent you, lm117.pdf, contains two things. It contains the data sheet for the LM117HV and also contains the application note in one file. Let me mention here the numbering system that National Semiconductor uses, where they use a 1 to indicate the military grade integrated circuit, and then he uses the number 3 for the commercial grade. There's also a number 2, not for this particular one, but for a lot of national parts, that is an industrial range of temperatures. For what we're doing, we're operating at room temperature, so either one is okay. Make this a little bit bigger. As in most data sheets, they start out with a description of the IC, kind of telling you what's good about it. And in particular, they'll pull out specific features. We'll be looking at some of these mostly through SPICE simulation. Of course, very typical to see an application right on the cover. This is probably the most common one, where you can have a voltage here, has a range of inputs, and the output is selectable by varying a resistor. We'll take a look at this one in just a little bit. Second page of the data sheet just has more applications on it. The third page has what we've seen before, which is tables of data, and also shows the temperature range of the particular parts. We'll be talking about these as we go through this chapter. Now, following these tables, typically you have a set of performance curves, which shows various parameters of the IC, sometimes versus temperature or versus different voltages. So here we got a thing called load regulation, current limit, adjustment current, thing called dropout voltage, temperature stability, minimum operating current, thing called ripple rejection versus output voltage, ripple rejection versus frequency, ripple rejection versus output current, output impedance versus frequency, line transient response versus time, load transient response versus time. We'll look at many of these through a SPICE simulation. And then after that is just more applications of the particular part. Let me jump ahead to page 12. This is the application note number 181, and it's actually describing the IC and giving a functional block diagram. Let's go back into the notes. Here's an example of what's called a basic regulator. It's probably the simplest use of the LM117, where I've got a voltage source called V in here, and simply going to ground the adjustment pin and take the output voltage. Let's go back and look at the previous page, see what's happening when that's occurring. Okay, so here I have my input, which is a voltage back to ground. Grounding this, and putting a load out here. have an open circuit initially, we can hook something else up to it. So I need to have a voltage here to power the circuit. And then what have I got? Well, I've got this feedback loop here. So whatever voltage is here, it's my reference voltage, it's going to show up across the load. Let's go back to page 2. And that reference voltage is about 1.25 volts. So what you got out here is a fixed voltage, given a voltage here that can vary. But there must be a minimum voltage across here for this thing to work. There's nothing else inside here, and so this is the piece of silicon, so I can't get more voltage out than I'm putting in. So this has to be bigger than this by what's called the dropout voltage. And that word is very descriptive. If you don't have enough voltage here, it'll drop out and stop working. So the voltage V in needs to be greater than the dropout voltage plus the reference of 1.25 in this particular circuit. Now most people don't want a 1.25 voltage regulator, and so this is the main application of the chip. So here put a resistor across here, put another resistor across here, but we'll allow this resistor to be varied. I was going to call it R2 no matter what value you set with the pot. Voltage across here, because we're just shorting these together, is going to have 1.25 volts across here. And that's going to cause a current to flow, which is going to be 1.25 divided by R1. And then the current that flows in R2 is going to be that current plus the current from the adjustment pin. We'll see from the data sheet a little bit that the current from the adjustment pin is pretty small. You can pretty much ignore this current compared to the current that's in here. If we go around this loop, the rise in voltage is going to be 1.25 plus R2 times this current plus a little bit of current, which is going to be 1.25 over R1 approximately. You pull out the 1.25 and you get a 1, and you have R2 over R1. It looks like kind of like a non-inverting amplifier equation with our R2 and R1. Now again, I have to have enough voltage at the input to support the output. The voltage here needs to be greater than the dropout voltage plus whatever the load is set to. So now I have a variable output voltage where I can pick whatever I want. The data sheet recommends using a 240 ohm resistor for this and then a 5K pot. Let's take a look at the range of values that can occur. Okay, the pot can be all the way to the top, which makes it 0. So in this equation over here, I can have 1.25 times 1 plus 0 over 240, and so I get 1.25 volts, just like our previous example. But if I put this pot all the way to the bottom, I get 5K. That makes this number 20.83, and so I get about 27 volts. So I have a variable power supply from 1.25 to 27.29. How big does the input need to be? Well, let's go take a look at the data sheet on page 4 and see what the dropout voltage is. So back to page 1 of our data sheet. Let's go to page 4, where we have curves. And one of those curves we pointed out before was called the dropout voltage. Let me make this a little bit bigger so that I can see it. Hopefully you too. So here's the dropout voltage versus temperature. So we're looking at room temperature, 25 degrees. Well, depending on how much current we're putting out, the dropout voltage changes. Let's take a look at 1 amp. When I have a 1 amp load current, I have a dropout voltage of 2 volts. Depending on what my voltage is at the output when this is occurring, my input needs to be 2 volts bigger. Now as the current goes down, that number goes down. And this is really basically the drop across those power transistors we saw back on page 1. So take a look at the case of 20 milliamps, which is this one right down here at 25 degrees C. That's about 1.5 volts. Go back into the notes. This is where I got these numbers from. So we use a data sheet to figure out whether our circuit will work or not. Our next application is called a precision current limiter. You can find this on page 10 of that LM117 PDF file that I sent you. Here a pot is placed across these two terminals, which is the output terminal and the adjustment terminal. We have 1.25 volts across here. That means we're going to have a current of 1.25 divided by R1. That current plus the adjustment pin current will flow into the load, but the current in here is very, very small. Let's figure out how much current is flowing in here if we were to use a 120 ohm pot. Take the pot all the way to the back. I'd have 120 ohms divided into 1.25 volts, and that'd be 10.42 milliamps. Now as I begin to move this pot towards the end, basically putting a short across these terminals, and they recommend having a minimum resistance of 0.8 ohms. Probably some series resistor stuck in here. Now, if you were to get there, what happens? Well, I got a very low resistance across that voltage reference, not directly, but through an op-amp circuit, and the current's going to go shooting up. There is a mode of the integrated circuit where it goes into current limiting, and we can see this on page 3 of the data sheet. Let's go back to our data sheet. So here's our dropout voltage. Let's go back to page 3, and you can see here there's a current limit. Depending on which package you're using, we'll be doing a SPICE model of the H package, and the typical value for the 117 and the 317 is 0.8 amps, which is 800 milliamps. There's also a graph on page 4 showing this current limiter where we stop at some value and limit the current. I'll talk some more about this one in a SPICE model in an upcoming lecture. Let's go back into the notes. And so that's what we're seeing over here, maximum current. You use the same circuit with just a fixed resistor, and you can make a constant current battery charger. If I put 24 ohms here, I'd have 52 milliamps. Let's take a look at page 11 of the data sheet. And that's the one right over here that we're taking a look at. Let's go back into the notes. I have a little story that goes with this. Many years ago on a Saturday, one of the ham radio operators was walking down the hallway by the 480 lab, and he looked in the room and he saw a battery, and the sides are bulging, and you could see the little isobars of heat coming out of it. He runs in the room as fast as he can. He pulls the wires out of the circuit. What was happening was someone had hooked up a battery charger and kept pumping current into a battery. The problem with this is the battery is going to get warmer and warmer and warmer as we pump current in it because there is some internal resistance. I don't know how long they were charging that battery, but if the sides of the battery were starting to bulge, you're about to have an explosion. He told me that he noticed that nobody in the 480 lab had safety glasses on. Why would they? It's a Saturday, nobody's around. You're lucky. Those people would have all been blinded by that acid flying in their face. So whenever you're doing a constant current charging of a battery, keep in the back of your mind, you need to monitor the temperature of this. And if the temperature gets too high, you shut this thing off. Let's take a look at page 11 of the data sheet again. You're showing a current limited 6-volt charger, and it says here that when you put a 1 ohm resistor here, you set the peak current to about 600 milliamps. Let's see if we can show that that's indeed the case. Here I've got a resistor across my output adjustment pin that's going to force 1.25 volts across the 240 ohms, and that current's going to flow in here. The current from here is very, very small, and we'll take a look at the data sheet shortly and just show you where that is. And so basically all that current goes in here, and so the voltage that we're going to get across the battery is going to be 1.25 times 1 plus this resistor divided by this resistor. That's about 7 volts. So for a 6-volt battery, we're going to be charging it a little bit bigger than 6 volts. Let's assume that this transistor is cut off. What does that mean? That means that the voltage across here is less than, say, 0.6 volts. If there's no current flowing, that means that this voltage across here is less than 0.6 volts. But what's the voltage across here? Well, it's going to be this current plus this current flowing into the resistor, again, assuming the current in here is very small. So what's the current in here? It's going to be 1.25 volts divided by 240, and whatever the charging current is. Well, that gets multiplied by 1, and say that needs to be less than 0.6 volts. Multiply the 1 through, I just get I charge plus 5.21 milliamps. We're talking about a fairly large current, so we just ignore this. And if you do, then we're talking about our 600 milliamps. So we verify that that indeed is the case. This is cut off as long as the current flowing in here from these two sources is less than 600 milliamps. Now what if it's greater than that? Well, let's see what happens. Let's assume the transistor saturates, and now the voltage across here is roughly 0.1 volts. Got roughly 0.6 here. So what's the voltage across here? Well, I got roughly 0.6 volts here. Let's neglect the drop across here. Say this is roughly about 0.6. So the rise in voltage has to equal the drops around the loop. So 0.6 has to equal something plus 0.1. That something is 0.5. Now what happens? Well, the voltage across the battery now is 1.25 minus 0.5, which is 0.75. So typically when you have a discharged battery, the battery voltage is pretty low. And so what's happening here when the current is very large is going to be the case when the battery is basically discharged. And so it's going to limit that current in the battery to be 600 milliamps as it begins to build up its voltage. And then once that current drops below 600 milliamps, the voltage will still be here about 0.75, then this thing lets go, and now the current just charges that battery up back up to 6 volts again. Take a look at that data sheet one more time to see what that current is in the adjustment pin. So here back on page 3 is the adjustment pin current. Is at typical value of 50 microamps. So again, pretty small. We've been neglecting it in our calculations. And this is a 3-terminal voltage regulator.